Hi again, everybody. This is the second video in our series of looking at how to take the matrix of an operator and by changing the basis of your vector space, put it into upper triangular form. If you want to see the first example, where we look just at 2 by 2 matrix, then just click the link here. Alright, so let's see here. Right. So we have an operator T, and the matrix with respect to some basis is given in this way. We're going to take the same approach as we did last time. We're going to just choose some non-zero vector and then apply the operator over and over again until we get some linearly dependent set. That'll give us a polynomial applied to the operator. We can factor that, and hopefully that'll give us some eigenvalues and some eigenvectors. Alright, so I'm going to start again by taking sort of the easiest vector, which is non-zero I can think of. I'm just going to take 1, 0, 0. Alright, by itself, of course, this is not linearly dependent, so I apply the operator, t, to it, and that's the same thing as just applying the matrix to this column vector. And that'll give me 3, 0, and 2. Okay, now I compare here and I notice tu is not a multiple of u. U is not a multiple of tu, so this is not a linearly dependent list. Okay, so I push on. I'm going to look at t squared u. Alright, so now I have to apply this matrix to this column vector. I'm going to get 9 plus 4 is 13. And then I'm going to get negative 4. And let's see, 6 and 2 is 8. Okay, so is t squared u a linear combination of u and tu? Well, looking very quickly at the middle row, I see there's no way I can possibly get negative 4 as a linear combination of two zeros. Okay, so I actually have a linearly independent list now. And since our original vector space was three-dimensional, notice it's a 3 by 3 matrix, I actually know that this is a basis for R3. But it's not the one I'm looking for. So, we move along. Look at t cubed u. So now I have to apply this matrix to t squared u, and let's see, I'm going to get 39 plus 16, which is 55. Let's see, negative 12 and negative 16 is negative 28. And then 26 plus 8 is 34, plus another 8 is 42. Alright, now, we'd said already that u, tu, and t squared u forms a basis for R3, which means there's no way that t cubed u isn't going to be a linear combination of the first 3 vectors. Alright, so let me stop here. Say, alright, how would I get 1 t cubed u to equal a linear combination of all those? Well, looking at this middle row, I say, okay, I have negative 28. I'm going to have to get 7 of those negative 4s. Alright, so I need 7 t squared u's. Now we go down here. I'm going to need 42, and I already have 56. So I need negative 14 more. Alright, so it means 2 times negative 7. Okay, now we go up to the top row. 55 is, okay, let's see, 91 and negative 21. That's 70. So I need negative 15 more. Since I have 1 there, I better put a negative 15. Okay, so if we write this down explicitly, t cubed u equals 7 t squared u's minus 7 t u's minus 15 u's. Alright, as we did before, I'm going to solve this for 0. And that'll give me t cubed minus 7t squared minus 7t minus 15, and let me put the identity operator. All applied to u is going to give me 0. Alright. I need to be able to factor this. So I think about the corresponding polynomial z cubed minus 7z squared minus 7z minus 15. And that actually can be factored. And here's how you would factor that. So if we had z cubed minus 7z squared minus 7z minus 15, well, I'll tell you, the way I figured it out is I noticed that if I put a negative 1 in for z, I end up getting 0. So I know I can factor out a z plus 1. I did a little polynomial division. I got a quadratic. That was pretty easy to factor. Alright, so I ended up with z plus 1, z minus 3, and z minus 5. All right, well, that's actually going to give me 3 different ways of factoring this in terms of order, at least in terms of what the first factor is going to be. So I'm going to write down here 3 different ways of factoring it. The first one, I'm going to put the z plus 1 first, only, of course, I'm applying this to t. So I'd get t plus I evaluated on, all right, we'll do t minus 3i after t minus 5i evaluated on u. All right, now before I write the other ones down, let's see why I'm happy. Well, that means that if I take this element, which, all right, this operator looks like a combination of t squared u's, tu's, and u's. And we know that that can't be 0, because this was a linearly independent list, at least the first 3 were. Okay, so I have a non-zero vector here, but when I evaluate t plus I on it, I get 0, which means this non-zero vector is in the null space of t plus I, and so I'm going to get an eigenpair. The eigenpair will have eigenvalue -1, and the eigenvector will be whatever this vector is. All right. Now, I could do the z minus 3 part first. So that would correspond to t minus 3i evaluated at t minus I, t minus, or t plus I, t minus 5i evaluated at u. And in this case, this equals 0, and this part does not equal 0 for the same reason. We knew that the first 3 vectors here were linearly independent, and so any linear combination of them, which is non-trivial, can't be 0. So this is a non-zero vector, but when you evaluate t minus 3i on it, you get 0. So this vector must be in the null space of t minus 3i. So 3 is going to give you an eigenvalue, and this will be the eigenvector. All right, we'll go down a little bit. There's one that we haven't put first. That's this z minus 5 term. So we'll go t minus 5i evaluated on t plus I, t minus 3i, u. And again, this means that we have an eigenvector for the eigenvalue 5. So we get 3 things here. We get an eigenpair, which is going to be -1, comma, well, that vector, whatever this is. This one gives you an eigenpair 3, comma, this vector. And this one gives you the eigenpair 5, comma, whatever that vector is. Okay, you can work out what these are. I'm just going to give names to them for right now. So I'm going to call this one V1, V2, and V3. Okay, why are these V1, V2s, and V3 so interesting? Well, I have 3 distinct eigenvalues, and I have an eigenvector corresponding to each of those eigenvalues. And we know that when you take eigenvectors corresponding to distinct eigenvalues, you get a linearly independent list. I have 3 of them. The vector space is 3-dimensional, so I must even have a basis. So V1, V2, V3 is going to be a basis for my vector space. Now let's take a look at what the matrix is going to be. So M of t with respect to V1, V2, V3 is going to equal, well, let's see, we'll put V1, V2, V3, V1, V2, V3. Now I apply t, and what is t of V1? Well, V1, remember, was an eigenvector for the eigenvalue -1. So applying t to V1 should just be -1 times V1. So I get -1, 0, 0 in the first column. And similarly, well, V2 was an eigenvector for the eigenvalue 3. So t of V2 is just going to give you a 3 in the V2 spot. And for the exact same reasons, t of V3 will be 0, 0, and 5. And so, as in the last example, we actually even end up with a diagonal matrix, but in particular, it will be an upper triangular matrix. All right, so you can click on here if you want to see the video with a 4x4, which adds a new wrinkle.